What if our picture of the universe is just a shadow of a more complex and wondrous reality? What if our familiar notions of the origin of galaxies, time and space are cracking under the weight of new discoveries? Today's science can no longer ignore the signals coming from the depths of space. They are too loud, too persistent, and too strange. Some discoveries make scientists hold their breath. They seem beyond logic, as if they've escaped from another era or even another reality. There are few explanations, but many hypotheses. Perhaps the key to these mysteries is already in humanity's hands. Get ready to peer into the abyss of questions that still have no answers, but are already beginning to change the course of scientific history. Don't forget to subscribe and like if you're ready to step beyond the familiar, into the unknown. In just 3 years of observation, the James Webb Space Telescope has become a source of data that is starting to change our understanding of the fundamental laws of the universe. A recent study based on images from the JWST project revealed a striking feature. The overwhelming majority of galaxies in the studied region of space rotate in the same direction. This one-sided asymmetry contradicts the logic of random distribution that would be expected in a neutral isotropic universe. Scientist Leo Shamir, after analyzing 263 galaxies, found that about 2/3 of them rotate clockwise. This ratio is far from equilibrium to be a mere coincidence. Moreover, such a pronounced preference can be noticed even without specialized training, as it is so clearly captured by the JWST's technology. What does this mean for our view of the world? Could it be that the universe had a directed rotation from the very beginning, like a giant mechanism? Or are we becoming victims of a subtle illusion caused by the movement of the Earth itself? Could this discovery explain why some galaxies appear older than the universe itself? And if the Doppler effect really distorts perception, how much can we trust existing methods of measuring distances and the age of objects? For now, there are more questions than answers. But at the same time, the James Webb Space Telescope is taking another step toward undermining the standard cosmological model by discovering a giant at the edge of the past that simply shouldn't have existed. Just 2 billion years after the Big Bang, JWST captured a colossal spiral galaxy, the Great Wheel, whose characteristics correspond to a mature structure that should have taken billions of years to form. It is 5 times more massive than the Milky Way. Its disk spans 100,000 light-years in diameter, and its rotational speed reaches up to 800 kilometers per second. The galaxy not only exists, but it already follows laws that were previously thought to apply only to mature objects. Its dynamics fit the Tully-Fisher relation, linking mass and rotational velocity. Such properties were a complete surprise because the existence of such a complex structure at such an early period calls into question everything we knew about the pace of cosmic evolution. Will we find traces of events that occurred even before the birth of our universe? What if the end of our universe is just the beginning of the next one? The question of what existed before the Big Bang led Nobel laureate Roger Penrose to propose the idea of a chain of universes, where each one precedes the next. In the 20th century, science transformed our view of the world from an eternal and unchanging universe to a model with a beginning, the Big Bang. However, this theory does not explain what existed before the beginning or how everything will end. Penrose suggested that the universe can only be considered a universe when there is movement within it. That is, at least 2 objects. When everything disintegrates and even light disappears, the universe will lose its measurable parameters and become a void, similar to the one that existed before the Big Bang. From this void, according to his hypothesis, a new eon, the next universe, may be born. What triggers the new explosion is unknown, but the idea provides an explanation for why our space is so homogeneous on large scales. If universes replace one another, this homogeneity could have been established even before our Big Bang, without an inflationary phase. To test the theory, Penrose suggested looking for traces of ancient cataclysms, for example, black hole mergers at the end of the previous eon. Physicist Vahe Gurzadian hypothesized that these events could have left marks in the cosmic microwave background radiation in the form of symmetrical rings with reduced temperature fluctuations. Such structures have indeed been found. However, the results remain controversial. Astrophysicist James Zibin points out that such data could also be explained within the framework of the inflationary model. Additionally, according to Hawking's hypothesis, black holes should evaporate long before any possible mergers, turning into energy. Supporters of Penrose's idea argue that this sea of energy is the material for the birth of a new universe. This leads to the idea of the multiverse, where universes may either exist simultaneously or follow one after another, transferring energy and traces of their past. Perhaps our reality is the result of such a transfer. Could the Hubble tension indicate that the standard model of the universe is outdated and that we are on the brink of new physics? How profoundly will the data from the Webb telescope alter our understanding of how the cosmos works? And could it hide the key to unlocking dark energy? Observations made using the James Webb Space Telescope suggest that the accelerated expansion of the universe may be caused by its unusual properties rather than measurement errors. Scientists from Johns Hopkins University have confirmed results previously obtained with the Hubble telescope, particularly in determining the distances to the nearest stars and galaxies. This calls into question existing cosmological theories, as the discrepancy between predicted and recorded values of the expansion rate remains unexplained. Nobel laureate Adam Rees emphasized the importance of this data, as two independent NASA instruments reached similar results. The study used the first 2 years of Webb's observations. Scientists analyzed galaxies with supernova explosions and compared the collected data with Hubble archives, ruling out the possibility of systematic errors. The so-called Hubble tension remains an ongoing issue. According to the standard cosmological model, the Hubble constant should be 67 to 68 kilometers per second per megaparsec, while actual measurements give values between 70 to 76 kilometers per second per megaparsec, with an average of around 73. The difference is too large to be explained by mere technical inaccuracies. Webb's results confirm the high precision of local measurements. The study covered about a third of the galaxies in Hubble's sample, with the discrepancy in values being less than 2%. Specifically, Webb gave a value of 72.6 kilometers per second per megaparsec, while Hubble measured 72.8 for the same objects. Work based on data from the SHA-0ES project and the Carnegie-Chicago program provided the most accurate distance estimates for Cepheid variable stars, key stars for calculating the Hubble constant. Although this value does not affect processes within the solar system, it is crucial for understanding the history and structure of the universe. Cosmologist Mark Kamionkowski believes that resolving the measurement discrepancy could shed light on other anomalies in modern cosmology. The standard model describes the development of galaxies and cosmic microwave background radiation, but it does not explain the nature of dark matter and energy, which make up 96% of the cosmos. Kamionkowski suggests the existence of early dark energy or other exotic forms of matter that could radically change our understanding of the universe. Why was the bright Lyman alpha radiation able to break through the dense fog of neutral hydrogen, defying existing models? Does this discovery imply that the first stars and black holes appeared much earlier than previously thought? Using the James Webb Space Telescope, an international team of astronomers discovered intense hydrogen emissions from a galaxy that existed in the very early stages of the universe's history. This discovery is puzzling, as such powerful light, according to existing theories, should not have been able to pass through the dense layer of neutral hydrogen that enveloped space during that time. The data obtained from James Webb challenges the established timelines of this process. Specifically, the galaxy JADES GSZ131, with a redshift of 13.0, was observed, corresponding to a period just 330 million years after the beginning of the universe. Notably, a prominent Lyman alpha line was found in the galaxy's spectrum, radiation produced by electron transitions in hydrogen atoms. Its intensity was unexpectedly high for such an early stage, as existing models suggest that the neutral hydrogen fog should have blocked this signal. Researchers believe that during reionization, light from such early galaxies could not spread freely. Only after the appearance of numerous stars emitting energy sufficient to ionize hydrogen did space gradually become transparent. This is why the detected Lyman alpha emission from JWST GSZ131 is particularly significant for understanding the processes occurring in the young universe. So far, scientists have not been able to precisely determine the nature of the light source. One possible explanation is the first generation of stars capable of creating a bubble of ionized hydrogen, which allowed the radiation to escape. An alternative hypothesis suggests the presence of an active galactic nucleus, where one of the first supermassive black holes might have formed. Further observations of JWST GSZ131 will help provide a more complete picture of what is happening and possibly revise fundamental concepts about the early universe. More and more data obtained from the James Webb Space Telescope are challenging traditional scientific paradigms and opening new horizons in our understanding of the cosmos. These discoveries could change our views on the origin of galaxies, the properties of dark energy and matter, as well as the early history of the universe. Each new step in this exciting exploration reminds us that the cosmos is full of mysteries that are just beginning to unfold. Don't forget to subscribe to the channel and stay updated on new research, as the science of the universe is just beginning.